All right, for example number 2, it asks us to evaluate the Riemann sum for f of x is equal to x cubed minus 6x, taking the sample points to be the right-hand endpoints, a equals 0, b equals 3, and n equals 6. And we'll come back to the b part in just a second. Now that a part is actually a review of things that we have already done. So if we have our equation x cubed minus 6x, a is 0, b is 3, and n is 6, then we could find our change in x by doing b minus a over n and get 1/2. So our first interval would go from 0 to 1/2, then 1/2 to 1, 1 to 1.5, 1.5 to 2, 2 to 2.5, 2.5 to 3. So there are our 6 subintervals. Now, some of you, when you do a right-hand Riemann sum, you just go through and pull out your right-hand endpoints. So you say, okay, I know to do my summation, I'm going to do f of x sub I times the change in x. So my change in x is 1/2. I can go ahead and slot that in every single time. To figure out the x values that are going in here, I'm going to pull my right-hand values out of the subintervals. So you just go through and you say, I'm going to use 1/2, 1, 1.5, 2, 2.5, 3. And you can see those are the values that we've put in here as well. Others of you use the formula, and if you're using the formula, then you need to identify x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, and x sub 6. So if you did that, x sub 0 would be 0, x sub 1 would be 1/2, x sub 2 would be 1, x sub 3 would be 1.5, x sub 4 would be 2, x sub 5 would be 2.5, and x sub 6 would be 3. And remember our formula for right-hand endpoints, you do not start with x sub 0, you start with x sub 1, and you end with x sub n, in this case x sub 6. However, if you were doing left-hand endpoints, you would start with x sub 0, and you end with the next to the last value, x sub n minus 1. So if this were left-hand endpoints, I would start by putting in 0, and I would stop with 2.5. In any case, if I want to find f of 0.5, that literally means put 0.5 in the place of x in this function. So 0.5 cubed minus 6 times 0.5 is going to give me a negative 2.875. Negative 2.875? Well, come over here and look at your graph. If you'll notice, this portion of the curve is below the x-axis. So yes, that y value is going to be negative. So if you take a negative height times your change in x base, you're going to get a negative area for this rectangle. And so we got a negative value for each of these first couple of pieces, and then we'll get a positive value at the end. It is possible then, when I tally these areas of my subintervals of my rectangles, it is possible to get a negative answer. That will happen when I have a larger piece below the x-axis than I do above. It's also possible to get an area of 0. Like if I had the same area below the x-axis as I did above the x-axis, that negative piece and positive piece would cancel each other out and I'd get an area of 0. So if more of the graph or all of the graph is above the x-axis, I get a positive area. If more or all of it is below, I get a negative area. Now, B is new to us. For B, they ask us to actually evaluate the definite integral. So we're evaluating from 0 to 3 that same function, x cubed minus 6x. Yesterday, we learned that the definition of a definite integral was the limit as n approaches infinity of the summation from 1 to n of f of x sub I times the change in x. So for that formula, we need to fill in two pieces. We need to fill in x sub I, and we need to fill in change in x. So let's start with change in x. Change in x is still b minus a over n. Remember that b and a come from your upper and lower limits of summation on your integral sign. So a is 0 and b is 3. So I can say b minus a, 3 minus 0 over n. My change in x is 3 over n. I do not have a value for n. They didn't tell me to just use 6 subintervals this time. So I do not have a number to put in the place of n. I'm going to leave a variable there for n that would represent any number of rectangles, 5, 10, 100, 1,000, whatever. All right, so if I were building intervals for this, then I would start at a, which is 0, and I would add the change in x, so that would be 3 over n. The next interval would start at 3 over n, add the change in x, 3 over n, and I would be at 6 over n. The next one starts at 6 over n, add 3 over n, and I'd be at 9 over n, and I could keep going with that process. So x sub 0 would be 0, x sub 1 would be 3 over n, x sub 2 would be 6 over n, x sub 3 would be 9 over n, and so on. So we have found the change in x is 3 over n, so let's go ahead and put that in the place of change of x in our formula. Now the only thing that we need to find is x sub I to fill in. X sub I, this formula is not in your textbook, but x sub I is going to be your a value plus the change in x times I. So for our problem, remember that a was 0, so we're going to have 0 plus the change in x. Now remember, change in x was 3 over n, so 0 plus 3 over n times I. So 3 over n times I would be 3i over n, so x sub I is 3i over n. So if x sub I is 3i over n, let's go ahead and put it in right here. So again, we said this was our definition of a definite integral. We only needed to replace x sub I and change in x. We had a formula for x sub I. We found it and plugged it in. We had a formula for change in x. We found it and plugged it in. Now, we've talked before about where the formula for change in x comes from, but this is the first time we've seen this formula for x sub I. Where does that come from? Well, it comes from a pattern that we can establish in these subscripts down here. If you'll notice, if x sub 0 is 0, x sub 1 is 3 over n. That's 3 times 1 over n. X sub 2 is just 3 times 2 over n. X sub 3 is 3 times 3 over n. So what we notice is it's just our change in x, 3 over n, times I. Because that's how many times we've had to add that change in x. That's how many multiples of it that we would have. So that's where we get the second part, change in x times I. The first part, the a value, we were fortunate on this problem that it started with 0, but let's say that our a value had been 2 here. Then I would have started at 2 and added the change in x, so this would have been 2 plus 3 over n. And the next interval would start at 2 plus 3 over n and would go to 2 plus 6 over n. So obviously I need to make concession for what if I don't start at 0, and that's why we need that a component of that formula. So now we understand where that formula comes from that we were utilizing down here. Okay, when we left off, we had the limit as n approaches infinity of the summation from 1 to n of f of 3i over n times 3 over n. We learned a property yesterday that said if you have the summation of a function times a constant, you can pull that constant out in front of the summation to make things less cluttered. So this 3 over n is a constant because remember, n just represents a number of rectangles. It could be 5, 10, 100, 1,000, but in any case, that would be a value, a constant value. So let's take 3 over n and let's move it out in front of our summation. So that's what we've done here. We've got the 3 over n in front of the summation. Now let's focus on what we've got left, f of 3i over n. When they give me f of 3i over n, if f of x was x cubed minus 6x, when they say find f of 3i over n, that means put 3i over n in the place of x. So let's come over here and put 3i over n in the place of x, put 3i over n in the place of x. So that's where we get what you see here, the 3i over n cubed minus 6 times 3i over n. That is from doing f of 3i over n. So we're going to replace f of 3i over n with what it's equal to. Now, let's do a little bit of simplifying. 3 cubed gives me 27. I cubed is right here. N cubed is right here. Minus 6 times 3 would give us 18, and then our I and N are still in place. To simplify some more, one of the properties we saw yesterday was that if you have the summation of two quantities that are being subtracted, you can break them into two separate summations that are being subtracted. And that's the next thing we want to do. Instead of having to work with this large piece, let's break it into two separate smaller pieces. So I'll have the summation of the constant times I cubed minus the summation of the constant times I. So that's what we've got, the summation of the I cubed piece minus the summation of the I. Now, this 27 over n cubed, again, represents a constant, right? So we could pull it out in front of our summation to get it out of our way. So you'll see over here, here's the 3 over n we already had, and the 27 over n cubed we just pulled out. The only thing that would leave then for the summation is just the I cubed, and so here's our summation of I cubed. Minus this second summation. Now we had the 3 over n out in front, so here's that 3 over n. This 18 over n is a constant, so it could be moved out in front of the summation, and that would leave just the I left for the summation, so there's our summation of I. All right, now let's do a little bit of simplifying here. 3 times 27 gives me 81. N times n cubed gives me n to the fourth. We learned yesterday that the summation of I cubed had a formula, and that formula was n times n plus 1 over 2, that whole quantity squared. So let's replace the summation of I cubed with its summation formula that we learned yesterday. All right, now we're ready to move to this next piece. Minus 3 times 18 is 54. N times n is n squared. And we learned a formula yesterday for the summation of I. It was n times n plus 1 over 2. So let's replace the summation of I with its formula, n times n plus 1 over 2. Now, it would be easier, looking at the second half right here, it would be easier to simplify this if I could put my numbers together and put my variables together. If you'll notice, in my denominators, I'm just multiplying. N squared times 2. N squared times 2 is the same thing as 2 times n squared. I could reverse that order and not change anything. So that's what I'm going to do with this second half. I'm going to switch n squared and 2. So that's what we've done right here. We've switched the order of the n squared and 2. That way we have the constants together and the variables together. We're also going to go ahead and distribute the n to the n plus 1. So n times n gives us n squared, and n times 1 gives us n. We want to do the same thing to the first half as well. I want my numbers together and I want my variables together. However, you'll notice that this component has a square on it. So when I take this 2 out of the parentheses where it's being squared, it's not a 2 that's going to come over here with the 81. It's going to be 2 squared, or 4 that will come over here into the denominator with the 81. So that's how we ended up, instead of 81 over 2, it was 81 over 2 squared. That gave us 81 over 4. The same idea with this n to the fourth. If I want to move it over here into this denominator, if I want this n to the fourth here, where the square is, I would have to rewrite it as n squared squared to be n to the fourth. One more time, if I'm going to move this n to the fourth, inside these parentheses, everything in the parentheses is being squared. So if I'm rewriting n to the fourth inside these parentheses, it would be n squared squared. And so that's what you see right here. N squared squared is my n to the fourth. And again, we're going to distribute the n times n plus 1. So that's where we're getting this n squared plus 2. All right, so doing a little more simplifying down to our next line, we could reduce these fractions. N squared divided by n squared is 1. N divided by n squared would be 1 over n. Everything else remained the same in this first piece. Then 54 divided by 2 is 27. N squared divided by n squared is 1. And n over n squared is 1 over n. What we're left with is a limit approaching infinity of constants and numbers divided by variables. If you remember our limit rules, we learned that the limit of a constant is that constant. So the limit of 81 over 4 is 81 over 4. The limit of a constant is that constant. So the limit of 1 is 1. The limit of a number divided by a variable when n is going to infinity is 0. So 1 over n is going to go to 0, and we keep our square. Then minus the limit of a constant is that constant, 27. The limit of a constant is that constant, 1. The limit of a number divided by a variable when n is going to infinity is 0. And now I can just simplify. 1 plus 0 is 1, squared is 1, times 81 over 4 is 81 over 4. 1 plus 0 is 1 times negative 27, negative 27. So 81 fourths minus 27 is going to give us negative 27 over 4. That is not an approximation. That is the actual area under the curve. That is the precise value. Now, example number 3, they ask us to do something similar. However, in example number 3, they ask us to give the setup only for this definite integral. We don't actually have to evaluate and come up with the numerical value. We just want the setup. So as I'm looking at this, I can notice that a is equal to 2, b is equal to 5. My integrand is going to be my function, f of x is equal to x to the 4th. So f of x, x to the 4th, a is 2, b is 5. So if I go through, remember my definition of a definite integral is the limit as n approaches infinity of the summation from 1 to n of f of x sub I times the change in x. I just need to find these two pieces. Let's start with change in x. Change in x is going to be b minus a divided by n. So b was 5, a was 2, so that'll give me 3 over n for change in x. So you'll see in the place of change in x, we've put 3 over n. Then we need to find x sub I. X sub I is going to be our a value plus the change in x times I. That was our formula from the previous slide. Our a value was 2, our change in x was 3 over n times I. So x sub I would be 2 plus 3i over n. So in the place of x sub I, let's put 2 plus 3i over n. Again, the idea behind that formula is if I were to create my subintervals, I would start with my a value of 2, and I would add my change in x of 3 over n. So the first subinterval would go from 2 to 2 plus 3 over n. The next one would pick up at 2 plus 3 over n, add 3 over n again, and I would be at 2 plus 6 over n. The next interval starts at that same place, add 3 over n again, and it goes to 2 plus 9 over n. So x sub 0 is 2, x sub 1 is 2 plus 3 over n, x sub 2 is 2 plus 6 over n, x sub 3 is 2 plus 9 over n, and so forth. Every one of them have that starting value of 2, so that we need our a value. Plus, each of them has had the change in x multiplied by however many times it was added. So here it's been added once, here it's been added twice, here it's been added 3 times. It is the same thing as the subinterval that I'm on. So again, that's where we get that formula, your starting value a plus the change in x times I, where you've added the change in x for however many number of intervals that you've gone through. All right, so once we created this piece right here, just as we did last time, we're going to take our 3 over n, which is a constant, and move it out in front of our summation just to make things a little less cluttered. So let's take that 3 over n and we've moved it out in front of our summation. All right. Now I need to do f of 2 plus 3i over n. If my function was f of x equals x to the 4th, if they say find f of 2 plus 3i over n, that means put 2 plus 3i over n in the place of x in that function. So I'll put 2 plus 3i over n in the place of x in that function. That would give me 2 plus 3i over n to the 4th. Now for this problem, because they said to set it up only, I'm finished. Because to actually evaluate this, I would need to take 2 plus 3i over n and multiply it out to the 4th power using Pascal's triangle or something of that sort. So that would be an elaborate process in itself. But when I finished, I would have an I to the 4th as one of my components. I don't have a formula for I to the 4th. There is a formula for I to the 4th, but they don't give it to us in our textbook because by the time we get to something that elaborate, we really should be using a calculator or a computer to do that computation for us. And so that's what they say for the B part of that problem, is to then put it into your computer and have it evaluate for you. We will put these into our graphing calculator to evaluate for us in a subsequent lesson. All right, last thing that we want to look at is example number 5. For example number 5 over on page 330, in the middle of the page they talk to us about the midpoint rule. And in essence, we find out that the midpoint rule is exactly what we've been doing when we were estimating the area under the curve using subintervals and the sample point that we chose. You know, sometimes we choose left, sometimes we choose right, sometimes we choose mid. When we choose the midpoint as our sample value, we are doing midpoint rule. So they just go back to what we've been doing and assign it a name. So for example number 5, they asked me to estimate the area under the curve. This is not going to be an exact value. So you can see down here, this is an estimation. It's an approximation of that definite integral. It is not the exact value. So they said use the midpoint rule with n equals 5 to approximate the value of the definite integral. So I can go through and say, okay, a is going to be 1 and b is going to be 2, and they've told me that n is 5. So I can say change in x is b minus a over n, so that would be 1/5, or if you'd rather use a decimal, 0.2. My first interval will go from 1 to 1.2, then 1.2 to 1.4, 1.4 to 1.6, 1.6 to 1.8, 1.8 to 2. There are my subintervals. When we use the midpoint, we go to each of those subintervals and choose the midpoint of that interval. So halfway between 1 and 1.2 is 1.1. Midpoint of 1.2 and 1.4 is 1.3, and then so on, 1.5, 1.7, and 1.9. So when we use our midpoint rule, or when we were finding our Riemann sum, when we were choosing our sample point to be the midpoint, we just chose x sub I to be the midpoint for each of the rectangles and multiplied it by the change in x. So we're going to do that for our 5 subintervals this time. So we can go through and say, okay, for the first subinterval, we'll plug in 1.1, and then there's our change in x. Second one, plug in 1.3, there's our change in x. Third subinterval, we plug in 1.5, change in x, 1.7, change in x, 1.9, change in x. So again, this is our height, and this is our base to give us the area of the rectangle. Now, if I'm looking for f of 1.1, that literally means take 1.1 and put it in the place of x in that function. So since this is the reciprocal function, it's just going to be 1 over 1.1. So down here we have 1 over 1.1. Since every one of these has the change in x, I'm just going to factor out that change in x out in front to save myself the work of multiplying by it every time. I'll just multiply at the end. So here we've plugged in 1.1 into the function, plug in 1.3, 1.5, 1.7, 1.9, and then we can come up with that approximation. Again, this is just an approximate value